Hi, in this video, it'll be our last video on the course on probability. I hope you have enjoyed the series so far, and let's begin. We'll talk now about some inequalities in probability, and what do I mean is that let's take the first one as our example. And so the first inequality we have in probability is known as the Markov Inequality. And it says that the probability that this positive random variable larger than A is less than or equals to the expectation of the random variable over A. And how do you prove it is that first we see that this following result holds true. That A times the indicator random variable is less than or equals to absolute value of X. And why? It's because if I equals to 0, this holds because this side is 0. And if I equals to 1, it means that X is larger or equals to A. And you can see if this is 1, A is larger or equals to is less than or equals to X. And so it holds because this preserves in either case. So now you just take the expectation of this whole thing. So E of this is less than or equals to E of that. And really the E of the expectation of indicative random variable just reduces to the probability. And then you just divide the A over and you're done. So it's really clear how to prove the Markov inequality. And I'll move on. So the next inequality we like to talk about is known as the Trebuchet Inequality. And that's if you have a random variable with mean mu and variance sigma squared. You can prove that the probability that X is close to mu is far away from mu by a distance of k is less than or equals to the standard deviation over k squared. And that's because we can see that X minus mu squared is a non-negative random variable, and so we apply the Markov inequality over here to get the following result. But since this portion is only true if and only if this is true, we can replace the inside variable with the following. And then this portion here is just sigma squared by definition. And so you get the Trebuchet inequality, which really follows from Markov inequality. And so I hope this is clear, and we'll move on to our next inequality. And that is the Jensen. So the Jensen have many applications. And because it relates an expectation, you can bound other expectations. And so if G is a convex function, then the expectation of Gx will be always greater or equals to G bracket expectation of X. And if concave, you just reverse the inequality sign. So the proof of why when it's concave is this really is because when G is concave, it means minus G is convex, and then you just need minus E minus here, minus out. The minus sign can take out, and then when you cancel out the minus, you reverse the inequality. So we only need to prove for the concave case. And let me just give you a picture first. So if it's concaving, it's like this, where all the tangent lines are below the graph. And so when you take a secant line between 2 points, the average shear will lie above the graph. So basically that's what it means. And so assume that G is convex, and then you let your mu be Ex and Y equals to A plus Bx, where A plus Bx is just the equation of the tangent line over here at this point. And so X is mu and Y is G of mu. And so Gx is larger than A plus Bx for all x by definition of convexity. quantity. And so you just replace this little x with a capital X for the random variable. And then you just take expectation and the result just follows accordingly. So there's not much complicated algebra, and it's really clear and precise on how to prove this. And so we take a look at some examples. So we can really say that the expectation of EX squared now is greater or equals to EX squared. And this means that the variance is positive actually, because now you just bring over. And this, because this is larger than this means it's larger or equals to 0. And we see that the expectation of absolute x is larger or equals to taking out the absolute function. And so really it helps us bound certain probabilities or expectations. So we can see the utility. So for the last part, we'll just go through this thing known as the sample mean to tie up any loose ends in causes in probability. So what is the sample mean? Is really you're taking a sum of random variables and then just dividing by n. And because these are all random variables, this sample mean now becomes a random variable. And so you can take its expectations and you'll see that it is mu, and for the variance of the sample mean is 1 over n squared times n sigma squared, which equals to sigma squared over n. And really it's very standard because you just need to expand out this part because they are IID, meaning they are independent. And really this really comes in useful when you're doing like statistic tests and you really need to do with all these means and stuff. So we like to take note that the sample mean is a random variable and there are a few properties that it follows. The first one is known as the strong law of large numbers, and that if you take the sample mean as you take more and more trials, this sample mean will approach the mu with probability 1. So it means in a very, very long run, the sample mean will approach the expected value mu, its expected value which is mu, with a probability of 1, so it will occur. But you take n, the limit as n go to infinity. And the proof of this you can find in the textbook. It's a bit long and technical, so I won't go through it for this simple course. But I hope you understand. It's clear why, because you're taking a sample mean, and so you want it to approach the expected value in the long run as well. And the next property it has is the weak law of large numbers. So in the previous one we have a strong law because we are showing that the probability becomes 1. For the weak law, we say that the sample mean is far away from mu by a distance of epsilon is going to approach 0 once n approaches infinity. Because by the strong law of large numbers, this is supposed to approach mu. So being away from mu by any distance will be 0, the probability. And so really we just prove this by using the Trebuchet Inequality. And as n goes to infinity, this approaches 0, and so it's bounded by 0, and so this approaches 0 as well by squeeze theorem. And lastly, this will be a very, very important tool in any probability course, any statistic course, and it is the central limit theorem. And this really gives us a way to find the distribution for the sample mean, even though we do not know what is the distributions of all the previous random variables. And it says that the sample mean will be approximately normally distributed. So the sample mean will be normally distributed with mu and sigma squared over n for a very large n. And the proof of the central limit theorem actually takes a bit more effort, but a simple case is given in the textbook, which I won't go through. So you can read it up if you are interested. But really, if you think about it, is that it's really like how when your teacher always says your grades are bell curved. So once you have a lot of people taking the exam, you're able to form the distribution, and then you will be more likely that more people do average as compared to everyone doing well. So it's really bell shaped. So it's really like almost normally distributed, the mean, when you take the mean of every sample. And so we can also write the central limit theorem as a sum instead of a mean, because the sum is just the mean times n, and n is constant. So it now just follows a normal where it's just n mu bracket n sigma squared. So I hope that's clear. And really, by taking this example, you see how it's really applied. But usually it's applied when you're doing hypo testing and stuff, when you want to test the random variable of the sample mean. And so let's take a very simple example, as like you throw a fair dice and we know each row is independent of each other. Sn denotes the sum of all the rows, and so we want to find the expectation of Sn and variance, which you can do as follows by definition. So that's quite clear. But really, if we were to find the approximate probability that the total sum of 100 rows exceeds 370, now we know that because the number of rows is large, typically more than 30 or 20, the sum of 100 will be approximately normal, and the expectation of S100 and the variance of S100 is as follows. And then we just find expectation of S100 by using this formula, and variance of S100 by using this formula. And then by applying CLT, since it follows normal, we just use our graphic calculator or any software, we can compute the probability. And so I hope it's clear how we use the central limit theorem, as it's a good way now to approximate a distribution for the sample mean. And that is really very useful in many statistical testing experiments. So that's all for probability. I've come to the end of this series. So feel free to check out my other series on calculus, discrete math, or any other ones that I've done on the YouTube channel. And I'll see you again. Bye.